Hello everyone. As I said, I will record a class today and you can watch when you are available. In our last class, we finished our last class talking about the HISTIC app pattern. And the HISTIC app pattern, it's also organic diagnostic horizon. It's an organic app pattern. The organic carbon content it's higher, equal or higher than 12% in the majority of cases, but we also saw that if we have some human action, this content could be equal or higher than 8%. So the content of organic carbon here is quite high, and because of this, we have a strong influence of organic matter, of organic carbon in the morphological, chemical, physical properties of the horizon. Okay, the HISTIC horizons different in opposite of the holistic horizon, holistic app pattern. The HISTIC it's formed under saturation, water saturation. So as you can see in these two photos, the HISTIC app pattern it's always formed close to the water table, and because of the reducing conditions, you have a strong and high organic carbon accumulation. Now let's see another a pattern, another diagnostic horizon, and in this case the melanic pattern. The melanic pattern, it is a mineral or organic pattern because you can register very low or very high organic carbon content in this case. So the organic carbon content could be equal or higher than 12% or much less than that, okay? Because the organic carbon content in this specific case is not the most important characteristic or the most important property in the soil. The most important property in the pattern in this case, they are the endic properties, okay? And I will talk about it in the next few slides, but let's just see some of these characteristics and what are the melanic patterns. The melanic patterns, they are composed of a mix of ash, volcanic ash, soil organic matter, loess, alluvium, and colluvial materials. So they could be formed by the mixing of several different types of parent materials, but what is the most important in this case is the sum of ash, volcanic ash. These volcanic ashes, they are more related to recent volcanism, like in Japan, in some areas in Asia, in some areas in South America, in some areas in Africa, in Europe, but definitely areas that volcanic activity it's quite recent and active, okay, producing ash, and after this ash be deposited at the surface of the soil, the ash could give some specific properties that are quite important to soil formation. In this picture you can see some layers. Of course it's quite hard to see only in a picture, but you can see different types of colors like this yellowish color, something like a grayish, dark and grayish again, and dark again, black. Well, all of these layers, they are different types of ashes from different types of eruptions, okay? So different volcanoes or the same volcano, they could produce ash, and this ash could be deposited at different times, and after this accumulation, soil can have some specific properties related to this melanic pattern. So you can see that the melanic pattern it's a type of pattern not because of human action, not because of organic matter activity or biological activity at the surface, but basically because ash deposition, okay? And ash only deposits at the surface. So it's why we call the melanic pattern as a pattern, as a topsoil, as a soil horizon that's formed at the surface, because it's related, it's straight related to ash deposition. And in the melanic pattern, we can see some specific and very important minerals. For example, allophane, hemogolite, ferrihydrite. These three minerals, they are called low crystalline minerals. These low crystalline minerals, they have specific properties that influence the melanic pattern, and they are straight related to volcanic ash. So the presence of these minerals promotes the endec properties that we will see in the next few slides. Okay, the melanic pattern can be seen in cool and humid sites with high amounts of aluminum and silicium. As I said, you can see then in the tropics, in temperate conditions, in periglacial conditions, no problem. The climate conditions is definitely no one of the soil formation factors that influence deeply the presence of the melanic pattern. But in this case, what is most important is the volcanic activity, a recent or active volcanic activity that produce ash and the ash deposition at the surface. Okay, so let's see now what are the endec properties, and then we can go deeply in the melanic pattern. Okay, what are the endec properties? These endec properties, they are related to the presence of those minerals that I said, allophane, hemogolite, ferrihydrite, and all of these minerals, they present very low crystallinity. So because of this, they have specific properties that are quite important and unusual. So, for example, they present a very, very high phosphorus absorption. So when you consider that primary minerals, they are related to low wafering as hemogolite, as allophane, these minerals, they usually don't present a very high phosphorus absorption. So for example, olivine, pyroxene, they usually present very low phosphorus absorption. But hemogolite and allophane and ferrihydrite, they present a very high phosphorus absorption. So they can absorb high amounts of phosphorus. So this is one of the characteristics that it's quite important because, of course, plants, animals, and other organisms, they need phosphorus to survive. But if the soil can absorb phosphorus in a high amount with a very, very strong chemical bonds, so you have less phosphorus that can be absorbed and used by the organisms. Okay, these minerals, they also present a very high absorption of water. So water can be strongly absorbed and retained by these minerals, the allophane, hemogolite, and ferrihydrite. So also you can keep a high amount of water in the soil, but you need to consider that a high amount of this water cannot be used by the organisms. These minerals, they present a very, very, very low bulk density. Okay, when you compare, for example, the pyroxene, olivine, and hemogolite, they present very different densities. Hemogolite and allophane, they present a very low density when I compare them with olivine and pyroxene. This means that the material, the soil material, will present a very low bulk density and will be quite light, quite easy to hand. Okay. Also, something that's quite important is that these minerals, they present a very high CEC, so they present a very high cationic exchange capacity, so they can absorb anions and cations in very high amount. I say anions and cations because it could absorb phosphorus and also calcium, magnesium, sodium, potassium in very high amounts. So they present a high specific surface and a high CEC that can absorb water, anions, cations. So the chemical behavior of these minerals is quite active when I compare to other minerals. It's why they are quite important, and it's why we call this as endec properties and then melanic pattern. Okay. Also, something that's quite interesting is that the pH of these soils is quite low. Okay, they are acidic, And why are they acidic? Because they release a lot of hydrogen during their wafting, okay? So the release of hydrogen decrease the pH, and this acidic condition can be seen in this kind of soils. So they can absorb a lot of phosphorus, water, they are light, they can absorb also a lot of cations and present an acidic pH. These are in general the properties that we can see in the endic properties and the melanic apetalum. All of them, as I said, it's straight related to low crystalline minerals like the allophane, immogolite, and ferrihydrite, and or some metal humus complexes also can produce similar properties, okay? In both cases, I need to identify them as endic properties, okay? But of course, the low crystalline minerals are much more common than these metal humus complexes. Here I can show you some photos, okay? This is a tephra. Tephra, it's a kind of rock that's formed by volcanic ash that this material, it's produced after diagenesis of and cementation of volcanic ash. Well, when the tephra starts to wafting, you produce some volcanic glass, and this volcanic glass can be seen in the soil, in the apetalum. But if the wafting starts to act on this volcanic glass, then you can find the endic properties in the soil, okay? The endic properties also can be distinguished between selendic and alluandic properties. Selendic properties, we have less wafting and higher contents of silicium, and alluandic properties, they are more related to more wafting or more intense wafting, and they're more aluminum than silicium, okay? So it's more common to see, for example, the yes, we can see different kind of minerals in this two conditions too. So for example, when we see the allophane is more related to aluminum. So we have this alluandic conditions, and the immogolite, we have more silicium, and then we have more selendic properties, okay? But both are inside the endic properties, okay? Both represent the endic properties. I'm just saying that because you can consider that this is the first stage of wafting when I found the rock. This is the median stage when I can see volcanic glass inside the soil, like this. Can you see this picture? You can see some grains like glass, and they are volcanic glass, especially this one. It's quite easy to see, okay? This photo I took on Japan. Only we can easily see some volcanic ash and volcanic glass formed by volcanic eruptions, recent and active volcanic eruptions, okay? But as I said, if this volcanic glass starts to be wafted and destroyed, then you can have some minerals like allophane and immogolite that can yield these endic properties to soil. So let's see the required criteria to endic properties, and this is one of the properties that I will pay attention, okay, because it's quite important. So first of all, you need to register a horizon that has less than 25% of organic carbon by weight and the fine earth fraction, okay, and one of or both of the items 2 and 3. So we have items 2 and 3. So first of all, the number 1 is mandatory. So I cannot identify a horizon with endic properties which has more than 25% of organic carbon or equal to 25% of organic carbon, okay? And these two, they are optionals, but at least one of them I need to fit, okay? That horizon that has endic properties should fit, okay? The first of all is a bulk density measured at 33 kilopascal water retention of 0.9 grams cubic centimeter or less. So I should register a very low bulk density, or I should register, and I should register a very high phosphorus retention of 85% or more than this. JJ, how can I do that? Well, you just need to mix a sample of soil with some phosphate, and you in the start knows the phosphate concentration. So for example, let's think that I can prepare a solution with 60 milligrams per liter of phosphate, and I put some soil inside this solution. I mix them and I keep them for 1, 2, 3 hours in contact, and after 2, 3, 4 hours I filter this solution, and then I measure the phosphate that's still in the solution, and by the difference I can measure the phosphate retention. If this phosphate retention is quite high, so 85% or more than this could indicate that I have minerals that has a very high phosphorus retention. For example, olefin, immogolite, ferrihydrite. Okay, and the other option is that I has an aluminum and half of the iron content extracted by ammonium oxalate that are equal or higher than 2%. Okay, so the number 2, I see that's and or, because this or it's related to the number 3. Okay, so for identify endic property in one specific app pattern, I need to fit this, first of all, this number 1, 35% of organic carbon, or less than 25%, I'm sorry, and I need to identify letter A, B, and C, or I should identify the issues, the statements at number 3. Let's see the number 3. They are 30% or more of fine earth fraction, varies between 0.02 to 2 millimeters in size. Okay, I can measure this very easily. The phosphate retention, it's 25% or more. Why I'm considering in this case that the phosphate retention could be much less than this, because now I'm considering that I have a sandier texture, or at least less clay in the material, considering this first statement. And because we have less clay, of course the phosphate retention will be less than the first case, or at least less than a clay rich pattern, a clay rich horizon. Okay, here is the same. If I sum the aluminum and half of the iron content extracted by ammonium oxalate, they should be equal or higher than 0.4%. In this case, the volcanic glass content should be equal or higher than 5%. You should remember I said that volcanic glass, it's only found in a medium case, so the weathering is not intense. Okay, in this specific case, it's quite common in periglacial and glacial areas in some temperate conditions, or at least when the volcanic activity and the volcanic ash and the volcanic glass, it's quite recent. Okay, and of course we need to fit something that's quite hard to measure. We only can do this after lab analysis, that the aluminum extracted by ammonium oxalate plus half of the iron content times this factor plus the volcanic glass content should be equal or higher than this value, 36.25. Okay, so you can see that all, or basically the majority of properties that identify the endic properties only can be identified or at least confirmed after lab analysis. So when you go to field and say, oh JJ, I think that this app pattern or this horizon has endic properties, well, you only can be 100% sure after lab analysis. Okay, the field work can provide some tips I will show in the next slides, but you need to run some lab analysis to be 100% sure about this specific property. Okay, Let's talk now about the Mellenic pattern. So just to memorize, now we talked about the index properties. Okay, the index properties is just one of the criteria of the Mellenic pattern. Now let's talk about the criteria to Mellenic pattern. Okay, so okay, and this. Okay, great. So first of all, I need an upper boundary at or in the first 30 centimeters, either of mineral soil surface or the upper boundary of an organic layer with index soil properties, whichever is shallower. So I need to consider that in the first 30 centimeters below the soil surface or below the contact with an organic layer, I need to identify index soil properties, that what we saw now, very high phosphorus absorption, low bulk density, sometimes even volcanic glass. Okay, so I need to identify the index properties in the first 30 centimeters or in this contact. Okay, and I need to identify the number 2. In layers with a cumulative thickness of 30 centimeters or more within a total thickness of 40 centimeters, all of the following. So I need to consider that too, that I need to register index soil properties in all of this 30 centimeters or more and a total of 40 centimeters. I need to register a very low value at 2.5 or less than this when the soil is moisty. So the soil should register dark colors, okay? And a chroma also should be 2 or less than this. So I need to register dark colors in this Mellenic pattern, and the Mellenic index should be equal or less than 1.7. Okay, this Mellenic pattern, it's a one specific lab analysis that we also run, and it registered the absorbance in different wavelengths, and it could distinguish humidified organic matter from grasslands and forests. So this Mellenic index, it's quite useful to identify if the material with very low and dark color that you can see, it's more related to immogolite, allophane, or just any other kind of source of materials, okay, mineral materials and also organic materials. Okay, so this Mellenic pattern, it's also something that we only can run on lab. Oh, and I forgot to mention the letter D, 6% or more organic carbon as a weighted average and 4% or more organic carbon in all layers. And you can see that's all of them and. So we need to fit all of these letters, A to D. Here are some pictures of soils with Mellenic pattern. You can see in this case this very dark color, okay, and this very dark color with very high water retention, very high phosphorus retention, presence of immogolite and allophane. We cannot see that on this photo, of course, because they are clay size particles, but you can see these very dark colors. This yellowish material, I can show you here. They have some grains, and these grains are volcanic glass too. This yellowish horizon, it's not a Mellenic pattern, but it register index properties, okay? So the Mellenic pattern, it's only here at the surface because it registers dark colors. It fits all the criteria to the Mellenic pattern, but the index properties, they can be found in other horizons too than only the Mellenic pattern, okay? So I told you that you register the index properties and you register the Mellenic pattern only with some lab analysis. So you need to run some lab analysis to confirm. But of course, we have some tips to identify the Mellenic pattern, or at least the index properties at the field. Okay, and what I learned from the Japanese soil scientists is that they use phenolphthalein to identify the material and also sodium fluoride. Okay, they take this filter papers and they embed them with phenolphthalein. So they keep them in a phenolphthalein solution for some hours, and after that they just dry it. And when they go to field, they take some pieces of soil and they smash this soil against this filter paper, and then they drop some sodium fluoride in over this material. When they drop, and you can find the allophane and mogolite, the soil gets this pinkish color, this pink color. Okay, this reaction is just an indicator reaction showing you that yes, you have here some allophane and immogolite. So probably you have endec properties, and if you are talking about a horizon with dark colors, probably you also talk about a melanic pattern. Of course, as I said, this is just a tip. This could be useful to identify these minerals at the field, but you need, after return from the field, run some lab analysis to confirm the endec properties and then confirm the melanic pattern. Okay, just a tip to, okay, let's see, I have a dark material that seems that register glass, volcanic glass, and I'm close to some volcanoes, so maybe I have some endec properties. Let's check. Okay, you can measure this at the field and at least select some horizons and layers that it's worth to run all the analysis to be sure that they can fit the endec properties and also the melanic pattern criteria. Let's talk about another pattern, the Moleck pattern. The Moleck pattern, it's a mineral soil material, so the organic carbon content, it's medium, definitely not high, definitely not higher or equal to 12%, okay? But you definitely have some organic carbon. You can see in this picture, in the first 30 centimeters, that you register a dark color, and this is the Moleck pattern, okay? And it's quite funny because you register a very dark color and something like a mix of white and black, and here you can see something very, very white, right? This soil profile shows you the typical Moleck pattern. The typical Moleck pattern has soil organic matter that stabilized by calcium. When you register a soil with a high content of calcium, the calcium can produce some metal complexes with the organic matter, and this difficulties, or this at least reduce the organic decomposition. Okay, it difficults the organic matter decomposition, so the microbiological activity it's reduced because this calcium can create very strong chemical bonds with the organic carbon, and then difficults or inhibits or limits the decomposition of organic matter. So because of this, you can produce some horizons with an median or even high organic carbon content, but definitely less than 12% of organic carbon. But you can find something like 6%, 5%, 4% of organic carbon. This is quite high, especially because the Moleck pattern can be found in some areas that register a dry climate condition. For example, semi-arid and even arid conditions, you can find them there, okay? Because the primary productivity it's quite low, and you think, okay, the topsoil should register like 1% of organic carbon or even less than that. But when you found a Moleck pattern, the content of organic carbon definitely will be much higher than 1%. As I said, it's quite common to find 5, 6, 7% of organic carbon in Moleck patterns, okay, because of the calcium. And calcium, it's an element, it's a chemical element that it's quite easy to be leached. So you cannot find very easily calcium, very high calcium contents in soils. Although you register a parent material that's rich in calcium. So it's quite common to find molecular patterns by the wafting of calcium-rich parent materials. For example, limestones, for example, basalts, because they register a lot of calcium-rich minerals, for example, calcite or plagioclase. And these two minerals can release calcium, and this calcium can stabilize the soil organic matter, as I said. But it's quite common that when you found this parent material, they also need register a low wafting and a low leaching. Sometimes you can find molecular patterns in wet and hot tropical climate conditions, but they are quite unusual. They are more common in dry lands, they are more common in periglacial conditions or temperate conditions, because you register less wafting and less leaching because you have less water, liquid water, okay? So they are more common in areas that you do not register a lot of rainfall, very, very high precipitations like 2,000 millimeters per year, 3,000 millimeters per year. Definitely it's not the place that you usually will find a molecular pattern. They are more related to areas that precipitation it's around 600, 800, close to 1,000 millimeters per year, or even much less than this, okay? So you need to find parent materials that are rich in calcium, and then this parent material should register a low wafting and a low leaching, or you will release all calcium and then you cannot form molecular pattern, okay? Oh, something that's quite interesting too, it's that humans can produce molecular patterns, okay? Humans can transform materials in some soils, and they can increase the calcium content and produce some molecular patterns, or as its most common case, you can find pristine conditions like just the natural conditions, the interaction between the soil formation factors create a molecular pattern, okay? And also something that's quite important is that in this specific case, we need to consider an average that's wave-fed according to the thickness of this specific horizon. I will talk about this in the next few slides, okay? So here you can see some pictures. The molecular pattern is this dark one. In these two cases, they are molecular patterns that were produced by humans, okay? They are not anthropic patterns in this case, because the anthropic pattern, it registered not necessarily a very high calcium content and a very high soil fertility. It's the case of the molecular. So we consider that if humans act in the soil and they increase a lot the natural fertility of the soil, so great, we need to consider this as a molecular pattern, okay? It's quite common in Europe, in Japan, in South America. In Europe, you can find, oh, of course, in North and South America, in both cases, you can find a lot of them, okay? Let's see the criteria for them. First of all, you need to find the structure units, pads or aggregates with a diameter of 30 centimeters or less than this, or a secondary structure with a diameter of 30 centimeters or less than this. What is the secondary structure, JJ? When you broke the pad or you broke the aggregate, sometimes you can find under other pads and aggregates. For example, in Brazil, it's quite common that aggregates of granular type, they compose a sub-angular blocky structure. So one structure, a group of pads with one specific structure, they can compose another kind of structure, a larger structure. Okay, we can see this in the field activities. And of course, in both cases, they should register 30 centimeters or less, okay, of diameter. or they should register a moderately hard or softer rupture resistant class. We will see this in the field work when you take an aggregate or a pad. You can try how hard is that aggregate or how hard is that pad. Okay, you just need to try to broke it using your tongue and toe and your finger. Okay, so you are trying to broke then using these two fingers, using this kind of movement. And the Molek Apollon should register something that's quite soft. Okay, you can easily broke the structure of a Molek Apollon. And why? Because the Molek structure, it's produced by biological activity. So it's quite common because of the animals inside the soil that they ingest and defecate soil, and because of the content of organic carbon, and because the interaction between calcium and organic carbon, that you create soft structures that you can easily broke using your finger. Okay, and in this case I need to consider and that at least I need to fit letter A and B, and if I fit one of them it's okay, but then I need to consider number 2, the rock structure including fine stratifications that are 5 millimeters or less than this of thickness. It's less than 1/2 of the volume of all parts. So if I found, for example, just one A horizon, okay, this A horizon should has less than 1/2 of volume with rock structure. Okay, if I register A1, A2, A3, each of them should register less than 1/2 of the volume. Okay, so we need to consider this. And that n value of less than 0.5 or a fluid class of a non-fluid. As I present previously, this specific a pattern also should register something like a solid behavior. Okay, this is a kind of lab analysis that we can run. It's not a big deal, it's not quite important, because hardly you will find something that has like a fluid behavior, but in some cases it's important to run this kind of analysis. Okay, other criterias considering the content of calcium carbonate, we define different colors. Okay, so if I register a very low calcium carbonate content, or even I don't register calcium carbonate in the soil, so the dominant color should register a value of 3 or less than this when moist, and 5 or less than this when dry. So the Molek Apollon should register a dark color. And the chroma also should be 3 or less when moist. So if I register no calcium carbonate or a very low content of calcium carbonate, that specific Apollon should register a very dark color with value and chroma here like 3 or 5 or less than this. Okay, if I register a higher content of calcium carbonate, for example, between 15 and 40% of calcium carbonate, in this case, the value and the chroma should be 3 or less than this when moist. And if I register a very high calcium carbonate content, for example, equal or higher than 40%, the value should be 5 or less than this. So the color should be less dark, or at least could be less dark. Why I'm saying that could be less dark? Because when I increase the content of calcium carbonate, of course, it's easy to understand that the soil should be lighter or whiter, registered white, more white colors, because the calcium carbonate has a white color. And then if I increase the content of calcium carbonate, hardly the soil can be very, very dark. It's why I consider that 5, it's okay in this specific case, okay? So every time that I'm checking the color of the Moleque apparel, I also need to check the content of calcium carbonate. If I don't register calcium carbonate, that's the easiest way to identify. So let's see, okay, let's check the color. But if I register calcium carbonate, so then I need to measure the content of this calcium carbonate and check the color, because the color could be 3 or 5 or of course less than this, okay? Other criteria, we have a lot of them. A base saturation should be equal or higher than 50%. So I should register a high content of calcium, of course, magnesium, sodium, and potassium, and I should register a very low content of acids like aluminum and hydrogen. So the CEC should register a higher content of bases than acids, okay? The organic carbon content should be 2.5% or more than this if the pattern has a color value of 4 or 5 when moist. So when the color is not too dark, I should register a high content of organic carbon. And if I don't register this very white color or very light color, I can see I can see these two options. 0.6% of organic carbon more than the sea horizon, if I have a sea horizon, if the Moleque apparel has a color value less than 1 unit lower, or chroma less than 2 units lower than the sea horizon. So if I register on Moleque apparel and the sea horizon, I will compare the color of both. If the Moleque apparel has less than 1 unit of chroma and 2 units of value compared to 1 unit of value and 2 units of chroma compared to the sea horizon. So I need to register at least 0.6%. What I'm saying this in a very easy way to understand is that in this specific case, the Moleque apparel and the sea horizon, they shouldn't register similar colors. If they register similar colors, so in this case, the Moleque apparel should register at least 0.6% of organic carbon, okay? If the Moleque apparel, or at least if the topsoil register a very similar color to the sea horizon and the organic carbon it's less than 0.6%, so it's not a Moleque apparel, it's anything else, okay? And the last option, 0.6% or more, and the apparel does not meet the qualifications in item 6A or 6B above. So if the soil register a darker color than 4 and 5 of value, and if the difference of colors between the sea horizon and the Moleque apparel is quite high, so I need to consider that the content should be at least 0.6% of organic carbon, okay? And more criteria, as I said, it's tough, and it's why I always said that you need to bring your soil taxonomy with you to the field, because it's quite hard to memorize everything, okay? And you don't need to memorize everything. So the minimum thickness of a Moleque apparel is 25 centimeters if the texture class of the apparel is loam fine sand or coarser than this. So if the clay content is not high, I should register 25 centimeters at least. Or if there are no underlying diagnostic horizons and the organic carbon content of the underlying materials decrease irregularly with the increasing depth. So if I below the Moleque apparel, I cannot see any other diagnostic horizons, only materials that register irregular content of organic carbon. For example, I register the molecule at pattern, and below of it I have a C horizon with, let's say, 0.8% of organic carbon, and below the C horizon 0.2, and below this other C horizon 0.8 again. So we have an increase and decrease of organic carbon below the molecule pattern. This irregular, this randomly increasing and decreasing of organic carbon according to depth should register that, okay, you have some fluvial or colluvial material here. Because of this molecule pattern should register at least 25 centimeters to be identified, okay? Or you can see here, or the number 3, any of the following, if present, are 75 centimeters or more below the mineral soil surface. So they are found below 75 centimeters or even more than this below the soil surface, okay? The upper boundary of the shallowest of any identifiable secondary carbonates or a calcic horizon, petrocalcic horizon, duripan, or fragipan, we will see everything else. So these horizons or these materials, they should be below 75 centimeters, okay? And or the lower boundary of the deepest of an anergelic, cambic, natric, oxic, or spodic horizon. So they need to fit the lower boundary of one of these horizons, okay? Or the app pattern should be only 10 centimeters if the app pattern has a texture class thinner than long fine sand when mixed, when considering all possible A horizons like A1, A2, A3, or just A1 if I just have one A horizons, and it's directly above a densic, lithic, or paralithic contact, a petrocalcic horizon, or a duripan, okay? All of these materials, we don't know yet what are they because I didn't talk about them, okay? But all of them, they're related to materials that hardly will allow root growing, okay? So when the molecule pattern, it's above something that it's something that could create a barrier to root growing. So in this case, the pattern could register only 10 centimeters, okay? Or of course 10 centimeters or less, it's okay, okay? The other option is that the thickness of the molecule pattern could vary between 18 to 25 centimeters, and the thickness is 1/30 or more of the total thickness between the mineral soil surface and the upper boundary of a shallowest of any identifiable secondary carbonates or a calcic horizon, petrocalcic horizon, duripan, or fragipan. So in this case, I need to consider the soil surface and the upper boundary of one of these horizons or materials, and I need to consider the total thickness, and to identify a molecule pattern, at least 1/30 of this total thickness should be equal to 18 to 25 centimeters, okay, and could identify the molecule pattern. The other option is that between the mineral soil surface and the lower boundary of the deepest of an argillic, cambic, natric, oxic, or spodic horizons, okay? We also didn't saw these horizons yet, so don't worry about it. You just need to consider that between the soil surface and the lower boundary of these minerals, I will consider the total thickness, and at least 1/30 of it should be equal to 18 to 25 centimeters, and this section fits the other criteria of the molecule pattern, okay? If I don't have any of this mineral or any of these horizons, so I will go to the last option. The thickness of the molecule horizon could be only 18 centimeters if none of the above conditions apply. So if I don't register something that could avoid root growing, or if I don't register any of these horizons, or materials. So 18 centimeters, it's okay. Okay. Guys, I understand. It's a lot of information. It's hard to fit some cases. I will share some exercises with you so it will be easier to identify these molecular patterns. Okay, I will present some data and ask you, okay guys, try to identify if this specific horizon is not or it is a molecular pattern. So you just need to check all these criteria and try to find the answer. Okay, don't worry about it. Oh, and a last of these criteria is that some part of the pattern is moist for 90 days or more cumulative days, okay, in normal years during times when the soil temperature at a depth of 50 centimeters below the soil surface it's 5 Celsius degree or higher than this if the soil is not irrigated. Okay, this criteria is just to show you that of course you are more related to dry conditions, but you need to register at least some moist conditions, some water in the soil. Okay, so at least 90 days of the year per year you need to register moist conditions. At least the soil should register some water, liquid water. Okay, so wow, finally we finished the criteria of the molecular pattern. It's a lot, yes, it's a lot, but don't worry, we will check then later again with some exercise, so I will be sure and you will be sure that you can identify them. Okay, let's move for the next one, the Pelagian pattern. The Pelagian pattern is quite interesting because it's a mineral soil material. So the organic carbon content, it's like the molecular pattern should be less than 12% of organic carbon. And the Pelagian pattern, it's something quite interesting because it's produced by humans. Also produced by humans, like the anthropic pattern. So it's quite interesting because this specific pattern, it's more related to long-term land use in low-quality soils in Europe. So in some areas in Europe, they are used to cultivate some soils, some sandy soils, acidic soils with very low organic carbon content and very low content of nutrients. And in this area, they start to add some material, some organic material, trying to increase the soil fertility. Okay, so they add sod and organic material at the surface of these soils, trying to increase the soil fertility, as you can see here. So this dark horizon here, it's something that was added by humans trying to increase the soil fertility. Okay, so you can see here, it's the both, here is the both case. All of these cases, they are related to organic material or sod or both that were added by humans trying to increase soil fertility. The criteria to identify this Pelagian pattern is that it should occur locally raised land in locally raised landforms. So it should register some terraces or landforms that were produced by humans, okay, and contains one or both of the following artifacts other than agriculture amends like quicklime and low fertility, okay, and they should register spade marks below a depth of 30 centimeters, showing that they were mixed by humans, they were produced and moved and transported by humans. Okay, other criteria, they should register a color of value of 4 or less than this when moist and 5 or less than this when dry, and a chroma 2 or less than this, so they should register dark colors as you saw in the pictures. It should register an organic carbon content that's equal or higher than 0.6%. It should register a thickness of 50 centimeters or more of materials transported by humans. Some part of the app it's moist in at least 90 days, okay, in normal years. If the temperature at a depth of 50 centimeters, it's 5 Celsius degree or higher than this if the soil is not irrigated. So again, as the Molek pattern, you should register at least some water during the year. The soil cannot be totally dry 100% of the time, okay? And this is a good question. A lot of students always ask me, JJ, how can we differentiate anthropic and Pelagian pattern if both are related to human action? Well, let's see. The process, first of all, the anthropic pattern, they are related to different types of land uses. And the Pelagian pattern, they are more related to ancient farmers that try to increase the soil fertility in some areas, adding organic material, okay? The material that's added to the soil, it's also something important. The anthropic pattern is more related to high calcium and phosphorus materials. When we talk about Pelagian patterns, the materials are more high carbonate and alkaline materials, trying to neutralize the acidity and increase the organic carbon content. The color is not something that's mandatory to anthropic pattern, but for Pelagian pattern, I should register dark colors. We saw then in the last slide. The thickness of these horizons, the Pelagian pattern asks you at least 50 centimeters, 50. It's much more than the anthropic, okay? Artifacts can be found in both horizons, in both patterns, and the organic carbon content is not a requirement to the anthropic pattern, but it's mandatory to Pelagian pattern. So both cases, it's also both patterns, they also can be differentiated according to the soil organic carbon content. So I can think in the process, I can think in the kind of material, I can think in the color, I can think in the thickness, and I can think in the soil organic carbon. We have a lot of criteria that helps you to differentiate both patterns, okay? Let's see now the Umbric pattern. The Umbric pattern, it's a mineral soil material too, so the organic carbon content, it's less than 12%, okay? And the organic carbon, in this specific case, will be stabilized by clays and aluminum. So I love to compare the Molek and the Umbric pattern because they are opposite sides of the same thing. Both registers dark color, both registers a medium content of organic carbon, but in the case of the Umbric pattern, we don't have the calcium stabilizing and creating a horizon with dark colors and average or median organic carbon content. In this specific case, what really helps the organic carbon stabilization is the clay and aluminum. The aluminum, such as calcium, also could create some chemical bonds, very strong chemical bonds that avoids the microbiological decomposition of organic carbon, and the clay can produce some physical barriers that reduce the microbiological activity of soil organic carbon. So both cases now can produce one other specific horizon, a pattern that's more related to acidic conditions, to deeply wetted and deeply leached conditions. Because of these acidic conditions, we have more aluminum, and this aluminum could avoid microbiological activity, microbiological decomposition, and because of the wafering, we produce more clay, and then we can produce some physical protection of the organic carbon, okay? The most important thing here that you can remember to differentiate Molek and Umbric patterns, it's about base saturation. The base saturation in the Molek pattern, we saw it's equal or higher than 50%, 50, and in the case of the Umbric pattern, it should be less than 50%. So all of these cases you can see are Umbric patterns. And let's see the criteria. Equal, in this case, it's equal to the Molech. You should register pads or aggregates with 30 centimeters or less. You should register a soft structure, something that can be easily broken when I do this kind of movement using my fingers. I shouldn't register a lot of rock structure. I should register something that has a solid behavior. The color should be dark. Of course, in this case, I don't have these options of different colors because this specific pattern, it's not related to calcium carbonate, so it's related to acidic conditions. So I don't have several options of colors. I just have one option that's 3 or less of value and 5 or less of chroma when they are dry. Okay, so we need to consider only this option of color. As I said, the base saturation is less than 50% in some or all parts of that specific pattern. And the organic carbon content should be 0.6% or more than the sea horizon, if this sea horizon is present and if the color of the umbric horizon is similar to the sea horizon, or 0.6% more and the umbric pattern, and the umbric pattern does not meet the qualifications of the item 6A above, and the minimum thickness. Now the minimum thickness is basically equal to Molech pattern. 25 centimeters if the texture is loam, fine sand or coarser, or let's say that we don't register a lot of clay in this horizon, or if we register underlying diagnostic horizons that are more related to irregular increase and decrease of organic carbon content showing some alluvial or colluvial material. The other option is that any of the following, if the present are 75 centimeters or below the soil surface, according to the presence of secondary carbonates or a calcic horizon. Sometimes it's hard, but sometimes you can see this umbric horizon related to this kind of materials when the surface, the topsoil, suffered an intense leaching and wetting. Okay, I saw this just once time on all my life. Okay, so it's quite common to find combination of carbonates and calcic horizon that register a lot of calcic, and the umbric pattern, not the Molech pattern. Okay, and in this case, if we register that, you need to find in that these horizons will be in the 50 centimeters below. Okay, so and the other option is the lower boundary of the deepest of an argillic, cambic, natric, oxic or spodic horizons. And the other options is just 10 centimeters if the pattern has a class finer than loam fine sand when mixed, and it's directly above a densic, lithic or porolithic contact, a petrocalcic horizon or a duripan. As I said, if you have something that avoids root growing, just 10 centimeters will be enough, and between 18 and 25 centimeters, it should be 1/30 of the total thickness between the mineral soil surface and something like this or that, basically the same of the Molech. And the last option, 18 centimeters if none of these conditions apply. So the thickness is basically the same of the Molech. The properties of the color, it's similar. The thickness, it's the same. The structure is the same. How softer the resistance of the material should be the same. The major property that's quite different now is the base saturation. I need to consider that the base saturation it's less than 50%. This is related to the landscape, to the conditions that create Molech and umbric patterns. And now let's see another pattern, the last one, the ochric pattern. The ochre pattern could be organic or mineral, no problem. It's related to the soil formation. It's related to the formation of aggregates and pads. So I don't see any other property that's quite important. Okay, the ochre pattern, it's used to add patterns to topsoils that they don't fit the other app patterns. So every time that I'm classifying the diagnostic horizons at the field, I need to think in the ochre app pattern in the last, okay, every time, because I need to try to fit that specific topsoil that I'm seeing at the field. I'm standing on the field. So let's see. It fits the criteria of anthropic, no, molic, umbric, pelagian. I need to melanic. I need to try all of them before think. Okay, this specific horizon, it cannot be classified as any of the other app patterns. So in this case, I will check about the possibility of the ochre app pattern. Okay, so you need to consider that the ochre app pattern, it's always your last option, is your last chance to classify the topsoil. Okay. So it could be formed by any kind of process like alluvial or illuvial horizons that produce clay migration. It could be related to any kind of mixture of material by humans like plume layers or the first 18 centimeters of an exhumed cambic or oxic horizons. So we don't saw these horizons yet. I will talk about this in the next classes, but when we have a cambic or an oxic horizon and they are at the surface, the first 18 centimeters I can call as an ochre pattern. Okay, and this ochre pattern, it could be a subsurface diagnostic horizon. In this case, when they combine with the cambic and oxic horizons. So it is the exclusive case that you don't have a mutually exclusive between the app patterns and the subsurface diagnostic horizons. So it's quite easy to understand. For example, when we saw in the other cases like here, this is umbric horizon. Okay, an umbric app pattern. Here we have the umbric app pattern, and here we have another diagnostic horizon. Okay, they are not one and the other at the same time. They are not together. They are not being classified together as an up pattern and a subsurface horizon. You don't have any superposition above app pattern and a subsurface diagnostic horizon. In this case of the ochre app pattern, yes, you can have this superposition between the app pattern and the subsurface horizon. You can have both diagnostic horizons in the same section of the soil. I will talk about this in the next classes when we talk more about the cambic and oxic horizons, and I'm quite sure that will be more clear than now because you didn't saw the cambic and oxic horizons, so could be strange, okay, quite strange to realize and understand this very well. So for example, this is the case. Okay, I have a very thin horizon that was produced by humans, or I have something that there's no dark colors or very high organic carbon content, and so it's not a pholistic, histic, or there's no very dark color or no strong structures as we saw. So let's see the criteria to identify the ochre pattern. So first of all, it should fit the definition of one pattern. And what's a pattern? A pattern is formed by surface process. So human action or primary productivity, organic and biological activity, ash and volcanic deposition, volcanic ash deposition. Any of these possibilities are related to one epipetal. So could fit one epipetal. So you need to consider if the material that you are seeing, that you are standing, is an epipetal or not, okay? And if you need to consider that's formed from pedogenic process at or near the surface, so okay, it's something that's quite easy to understand, that okay, I'm seeing that this specific horizon, it's quite related to biological activity. Most of the rock structure, including fine stratification, has been destroyed, so I cannot find a lot of rock structure in that specific section. It has been darkened by organic matter and or shows evidence of alluviation. So the partial decomposition of the organic matter gets dark color to that specific horizon, and or I can see some evidence of alluviation, some evidence of clay removal of that specific section, and it falls to meet one or more of the required characteristics of any other epipetal. So I cannot call something as an ochreic epipetal if that specific section fits all the criteria, for example, of a molic epipetal, or an umbric epipetal, or a pholistic epipetal, or a histic epipetal. So I only can call as an ochreic epipetal if the properties that I register in that specific horizon that I'm seeing and I'm trying to classify, they don't fit all the requirements for the others, for the other epipetals. Okay, so I need to be sure about this. It's why I'm saying that you always need to be sure that you only will classify, at least think about the ochreic epipetal after excluding all the other possibilities, all the other epipetals. Okay? And the only criteria that we really need to consider is that the ochreic epipetal has at least some water during 90 days or more during normal years. In the first, if the first 50 centimeters has a soil surface if that it's equal or higher than 5 Celsius degree and the soil is not irrigated. Okay. So again, here we can see all the epipetals, all the options. The anthropic, strong human action; pholistic, high organic carbon content in non-flooded areas; histic, high organic carbon in flooded areas; melanic, volcanic glass or ash; presence of allophane, immogolite; molic epipetal, organic carbon, it's stabilized by calcium carbonate or even calcium. Ochreic, it's that specific epipetal that doesn't fit any other. Pelagian epipetal is an anthropic epipetal formed by humans, induced by trying to increase the soil fertility, adding alkaline materials and organic carbon materials. And the umbric epipetal is also a horizon that's formed by stabilization of organic matter by a metal, but in this case it's aluminium, and clay activities and clay minerals, trying to physically protect the organic matter, the organic carbon. Okay, so they are quite different from each other. They are not similar. If you understand why and how they are different, it's okay for me, not a problem. You don't need to memorize all the criteria, but you need to memorize the general characteristics of each of these epipetals. Will be much more than enough. Okay. So guys, I will finish the recording now. In the next class, we will start to see the other diagnostic horizons, the subsurface diagnostic horizons. See you on Monday.